tunnel was the biggest challenge because it was passing through a thrust in the Himalayas, and the overburden available overburden on the gradient of the tunnel was more than a kilometer, which itself was a challenge. But after completion of this tunneling project, the distance between Manali and Lahore has been reduced by about 45 kilometers. And the time, what is important is not only the distance, it is the time. And this time has been reduced by about 3 to 4 hours because we used to otherwise cross the Rohtang Pass. Similarly, taking up number of projects, and we intend to uh, connect Leh throughout the year uh, through this by constructing a series of tunnels, and that would be one of the greatest achievements in this area. See, like today's coming to the today's virtual training session, we have this virtual training session by Mr. Bio, who is a very young professional, and uh, he would be talking to us about managing the risk of tunneling projects through different procurement methods. We are grateful to Mr. Bio, and let me tell you, Mr. Bio is a very active young professional when it comes to young professionals in the area of tunneling. Young Professionals Association, also in International Tunneling Association. And I would also like to acknowledge that NHIDCL is also part of this virtual training session along with Tunneling Association of India. Now, I would like to thank Mr. Bio for taking out time, and I hand it over to the organizers to take it further. Mr. Sharma, are you listening?
Yes, sir. Now we can start this session. Can you please share the screen so that the speaker...
Mr. Bio, I will request you to please share your screen and start the training session. Thank you.
So, hello everyone. Here is Giuseppe Gasp speaking from Canada. Can you everybody see my screen first of all?
Yes, it's visible, sir.
Perfect. So I'll move a full screen. And first of all, I want to thank the Tunneling Association of India for inviting me, and in particular the president and the vice president, and my good friend Sandeep, who is leading the young members as well, to invite me. I want to thank Mr. Devendra very much for still thinking of me as a young member. I am also closer to 40 years older than to the threshold limit for the young members, but I look young, so I think it is a great compliment. Thanks for that.
You're very young. Looking at me, I've already crossed 60. So in fact, you're very young. Thank you.
So I would like to get these training session started with the safety moment that is common for us here in North America to have. And my safety moment for today is that of sipping some water. So I'm going to have a glass of water all the way through this workshop. And I would gently request that every one of you kind of remember with this safety moment the importance of drinking water. We're now working from home, most of us, all over the world. And sometimes we are so much concentrated on our work, we stay on our desk for many hours, and we forgot to sip some water sometime. So everybody knows how much is important the water. Our body is made of water mostly, and it makes us feeling better, more energetic. And research experts say that 2.5 liters is what we should need every day to maintain our health. So we're going to go through the presentation, and sometimes I'm going to stop and request everybody to sip some water as well as I will do. Now, first of all, some acknowledgements. The lecture today comes from experiences in my past 15 to 20 years, and I've traveled the world, built tunnels everywhere. And particularly today, we're focusing on some relevant examples that will help me through the concept I will express. There are here a number of companies and people from which I learned a lot. You may recognize some of them from India, because I had 5 years of experience between Bangalore Metro, Delhi Metro, and Mumbai Metro. And I want to acknowledge what I learned from all of those people and professionals in my lifetime. The outline of the presentation will be that of starting with a little bit of understanding what do we mean by traditional and alternative delivery. We will move into working out the balance between risks and benefits in tunneling project, and then finally looking at the correlation between the risk management plan and the different procurement methods. So I'll try to express what is the impact of having a different type of contract with the owner or with a contractor or with a consultant, and the risks correlated with the geotechnical investigation, the data report, the baselines, and how we can balance and mitigate those risks in these different contractual environments. I'm going to have some lessons learned from case histories, and the case histories you will see through the presentation are coming from the Bangalore Metro Underground Contract 1 that has been completed, and now the metro line is operational. As you may know, it's the north-south line in Bangalore. I will speak about Istanbul Metro, Kadıköy-Kartal, which is a 30-kilometer long subway on the Asian side of Istanbul. And then about the Brenner Basin Tunnel, which is the longest tunnel in the world, which connects Italy and Austria and is currently being built. We're going to have some questions and answers and final remarks. Now, to get started, let's set a little bit of ground rules here. What we usually globally intend for traditional delivery is the one where the owner of an asset, when decides to move into a tunneling contract, establish two different separate type of contracts, one with a designer and one with a contractor. Now, in Europe as well in Asia, this is not very popular, but in North America it is, and as well as in UK. The owner has all of the responsibility for the geotechnical investigation and for the preliminary and detailed design, to the very issue for construction drawings. And this is why the designer that is in direct contact with the owner often has a number of subs, either consultant or those subs that are developing the geotechnical investigation program. A separate contract, once the design is completed, is then established between the owner and the contractor. The contractor may still have some subcontractor or some subconsultant as designer, but he's the only entity having a contract directly with the owner. When we move into alternative delivery, we used to speak about different type of forms of contract. Design and build, very popular in India, and P3, for example, which are more and more growing everywhere globally, or other alternative deliveries that I'm going to speak about in a little while. This type of relationship is, as you see, easier somehow, more direct, and has a direct relationship between the owner and who builds the asset, which is the design build, sometimes financing entity. This design build entity is then constituted by designer or designers and subcontractors specialized in doing other tunneling operations or station constructions, ventilation systems, whatever it's needed. But the one thing that is different between traditional and alternative delivery is this either dual or unique type of contract relationship with different entities, designing and building the contract. Now, what is the difference in terms of schedule within the two methods? We are all acquainted with the design build method. I myself deliver a few projects in India with the design build method, and it is quite efficient. It is confirmed globally that we have average time saving of about 33% and average cost saving of about 6%. This is because the whole schedule is quite concentrated within an initial quick planning, but then the preliminary and final design take place as the estimation and bid from the contractor participating to the tender phase develops, and then the permit acquisition doesn't have to wait for the completion of the final design, but will start earlier in the game, so that construction can actually commence about 30% times earlier than what happens with the design bid build method. The design bid build method is very popular in some countries in Europe and in North America. It is more linear, and as you see, allows the owner to have a full control over the whole. We have a preliminary design followed by final design, then a cost estimate, then we go out to bid, and the bid is only for construction. Once we have the awarded contractor, then he will get the permits done. And finally, the selected contractor will go into site and get the construction done. So you see what changes here is really the time in which the cost of the project is determined. While on one hand, for the design bid method, it is left to the contractor to estimate it based on their own design. On the design bid build, this cost is determined much later on in the game because there is a separate contract, as I said before, with a designer, which is developing the design directly for the owner and not for the contractor. In North America, we have been looking also at some of these design build proposals, and we can confirm as AECOM also that a fixed price design build project are actually savings about 21%. So it's very much in line with what we said before, even more, because I said in globally average is 6% savings. In North America, we have seen that we may save even more, 21% in terms of total cost of the project. And you see here a number of examples that I collected from our experiences to confirm this data. In the United States, it is more and more popular to move design and build, but not every state of the United States is having a legislature, a code that establishes how to work on a design build environment. As you may notice, we are talking about no more than 10%, more or less, of total projects that are delivered with design and build, but it's a growing process. In the past years, from 2013 to 2017, we're moving from 8 to about 12%. Now, the green, dark green states are those that have a current existing permitted way of building contracts in tunneling with design and build. The ones in gray, they have very limited potential, and the different colors of green will show you states that are so and so open to design and build projects. Now, what is the advantage here, and why do we move design and build or design bid build? Now, really, having one contract between the owner and the design and builder as a single point of responsibility. And that one point of accountability is what allows the legal framework to be much easier. Now, the design builder can take many forms. We can either have an integrated design build firm with all services in-house, including construction and design, or we can have a joint venture, or we can have a contractor hiring an engineer. But who is taking the lead here? And that's what really is important, even when we are experiencing about design and build contracts, to understand, because proven ability to deliver a certain type of project is what it really matters. I've seen several times in my lifetime contracts being assigned and being led by entities who were not really experienced in tunneling. When we speak about tunnel, we want to have the lead as one of the team members who has more experience and more ability to deliver a tunnel, even though may not be the strongest of the financial partners in the joint venture. And that's what is a first critical message to deliver in this presentation. Now, let's look, however, what I mean by alternative delivery, because there is not just design and build. There is a number of them. First of all, you see the CMR is the one that is actually still having a difference between the designer that is working for the owner and the contractor which is building the contract. So in this case, we have to distinguish what we mean by build as design and build to perform. So really, we are talking about an owner which is ultimately still the one that adjudicates between the design and the construction issues. So it is not really yet a full alternative delivery, because there is a lot of responsibility on the designer side and on the owner side, because they're still having the risk of the geotechnical investigation. In a progressive design and build, instead, the geological geotechnical framework is only general in nature, and the contractor and their designer is then requested to advance the geotechnical investigation program during their own contract. However, the time and material form is often adopted, and for this reason, even though we have an early contractor involvement, yet the interest in the contractor in reducing the overall cost and schedule is quite limited. On a lump sum design and build, that's the typical contract we used to see. We have a draft series of information on the design, and then as contractors and designers, we are requested to do a detailed design, cost it, and then being responsible for the cost we decide to put in during the bid phase, unless there are claims for unexpected geological conditions or differences on the site that were not known at the time of the tender. A design build operation is a new form, more and more common, which includes a financial component. So the design build team has to approach banks, financial institutions, and get funding because they will need it to operate that line, subway line, or that sewer. We're talking about tunnel projects here for an amount of time before handovering it to the owner. And finally, we have the P3, the public-private partnership. So in these cases, we have a direct intervention of the public, partly financing the works, but the private entity will actually have full responsibility of geotechnical investigation, design, construction, maintenance, and operations for an amount of years which is directly proportional to the investment that the public is developing. Now, I hope this made a little bit more clear the distinguishing of different type of alternative contracts and what really is the reason why we don't move alternative delivery in North America while somewhere else in the world, such in the Indian area, we have a lot more accomplished with this design form. Well, first of all is the fact that many states, as I say, don't have a proper legislation to allow that. There is also sometimes a lack of ability in selecting the design builder based on qualification and experience, just because there is not many competitors locally, perhaps, that can deliver a tunnel. And that's why we're seeing, particularly in Canada, a lot of contractors and companies coming from abroad, from Europe, from Asia, coming in and bringing their experiences and qualifications on projects that maybe is the first time that they have been built in such a way in Canada or the US. Now, what is also critical is that the involvement of design and builder earlier kind of shorten the time to complete the project, but also open to a number of liabilities that very often the owners are not ready to take on. Now, that's the time for a sip of water. And I wanted to make polls, but we won't have the ability to poll it. So these are mostly polls to just think about that. And first of all, I wanted to ask you, how do you quantify your involvement in alternative delivery? As you see, different answers were possible. I'm not asking you to answer, but to answer to yourself. But I want to tell you that when I have given this workshop in some other situations in other countries, well, there are very few people that really can claim they have delivered more than one alternative delivery project. And I'm sure that in this environment instead, in the Tunneling Association of India, we have a lot more experience in that. And the second poll was to understand better what is your background. But I'm sure that as every other tunneling association in the world, you have a good understanding from both the private side and the public side. Now let's move into the second section here. The first tunneling. So there is definitely the need, as our vice president said before, to develop an underground world habitat. Developing countries are even more interested in underground space because of the crowded cities that they may find. And this is the example, for example, of Bangalore. When I remember I was there about 10 years ago, it was a country that every year was kind of doubling the population in the previous years, in the previous decade. And this intense immigration makes our cities, not just in developing countries, but also in developed countries, extremely unfavorable for life. And that's why the use of the underground space is more and more critical. The growing of the economic cannot actually create danger for life in terms of pollution, noise, and traffic congestion. And that's why we need to find a solution to that, which is that of actually using the underground space more responsibly. As you may notice, there are different layers. The first layer is usually adopted for utilities and common services. But then below that, we have public transit, which is either through trains or subways, and then below even rail and road networks may happen. And at lower levels, that's the new development type of space. We may have caverns for either working facilities, industrial facilities, in order to shorten the distance between residents that are on the surface and workplaces, which may actually happen underground. And then finally, reservoirs. We all know how important water is and how important water will be. So many cities are actually creating those reservoirs. I think about Singapore is one of those that are creating those underground reservoirs for water. And these are done by tunneling methods most often. And that's when we come in the picture to find those solutions for our growing cities. Now, the need to develop an underground water habitat definitely requires us to look after how to make these more livable. And again, those examples are coming from the Bangalore Metro, where large cutouts were created in the stations, side walkways along the stations were needed in order to allow people to easily manage the underground space. There is no light, there is no sun, and we need to recreate that type of effect of being overground to make people more comfortable in using underground space. That was the first underground subway in Bangalore, and many people would have never actually felt comfortable going underground. And this is important to consider also. What is the social impact of our asset, and how we can make it if they've never been using an underground space before. Now, this is an example from San Francisco on how the environment can be considered a key component of our underground space, both in terms of allowing the light, but also in terms of allowing, for example, the heat or the climate conditioning in the underground space. And in this case, there was a zero emission station that allowed for a direct interface to the surface and direct exchange of heat and cool air through the underground geothermal properties. Quite interesting project indeed. Now, it is all good speaking about how advantages to underground, but we also must consider the risks of going underground. You probably remember this example from Singapore, the Deacon Highway disaster. That is one of the examples where poor geotechnical engineering and tunneling engineering, as well as construction issues, may create damage and endanger the life of people. And we don't want this to happen. It is not just the famous example of Singapore. Every day in the world, there are some of those issues, and they don't look good for us in terms of industry. So we want to find a way that we can manage those risks properly across the different procurement method we have. But to do that, we need to understand what are the risk factors and where do we find them. So I have built this matrix that help us understanding, starting from the top and moving clockwise, how to identify the risks. And I have identified 6 areas where those risks may be concentrated. First of all, on a political legal level, we need organization and governance. We know projects may stop as political interest stops on those projects. And that's why we need to be able to mitigate them when we consult with the owners, when we consult with the government, to understand what is critical to limit those risks. What do we need to have in the ground early in the game to avoid that a new political intervention in future may stop the project just because the interest is less? Then we have a supplier power. Now, this is mostly speaking to the procurement method, and is the fights between the contractor and the owner, or between the designer and the contractor, in order to try to have more power within the game. And this is a major risk that also needs to be accommodated. Moving from the market progressively to the management side of this quadrant, we may think about an economical impact. We have seen now with the COVID-19, many public investors limiting at the beginning their investment on the underground project just because it is more expensive than an overground one. And this is also another risk we need to consider and mitigate by telling the governments and the property owners that there is less risk in going underground than overground, so that they will be more comfortable allowing those projects. And then we can move into more the execution phase, where we have investigation, design, and monitoring. This is more typical for us to work on. This is on a contractual basis, as well as what are the impacts on the environment, the health and safety, and the stakeholders. But finally, what we need to consider is what is the social quadrant of those risks. So during the operation and maintenance, what will be the cost? What will be the final user understanding of the underground space? And that is something that also creates some risks. Now, we can definitely manage the risks. We can reduce the probability and the impact of those risks to reduce the overall risk impact, but we cannot deny that some of those risks may always exist. And actually, all of them will always exist. We can only try to control them better. And by moving into alternative delivery method, this is very much on the designer and the contractor, while staying on the traditional delivery method, this is more on the owner side. And let's see why. It is all about the type of design. when we are on what we call the traditional design bid build, the design is very prescriptive. And as I said before, most often the owner goes as deep as in detail as the issue for construction drawings. But moving towards a design build approach and even a public-private partnership, there is a shifting of risks from the owner towards the contractors, because there is an increasing complexity, an increasing number of stakeholders and interaction that requires the private financing and a private exposure towards the risk. But these open also to innovations, to new ideas, to the application of cutting-edge technologies that an owner which is risk adverse will never allow due to the risk tolerance that they need to respect. But a contractor and a private entity more open to gain value out of a contract may be actually more interested in implementing new technologies and approaches. Now, that's why an improved collaboration between all of the entity is really required as we move forward into more and more public-private partnership or design build approaches with respect to more traditional deliveries. What is critical at this point is really mentioning the observational method. Now, we used to design our tunnels predicting with our design analysis what will be the behavior of the ground and the soil structure interaction underground. And then we monitor what happens on the underground structure to make sure that we are doing a good design and the construction is safe. But this is not enough. Not only the underground structure, the tunnel needs to be monitored, but also the surrounding ground and the structures above, the utilities, the buildings over the ground. So we really need to move into a flexible approach where not just we observe, but we modify the design, and we are able to apply predefined countermeasures to limit our possible damage on the surrounding areas under threshold values. Now, this is not even enough. We need often to develop a program for advancement of tunnel, which is really the one that allows not only to apply predefined countermeasure, but to adapt them. And the digitalization of our processes is what allows this constant understanding of what is happening in the ground, what could be the best means and method to adapt our construction to the real conditions we find on site. And this flexible approach, plus the program of advancement of tunnel, together with the observational method, are what really are the foundations of our full risk management plan. Having defined that, let's move into an example of how this applies on a public-private partnership example. Now, you see the public owner is up there and will be the final owner of our underground asset, like BMRCL or DMRCL, the public entity. So that what they do often in Europe and North America is hiring a concessionaire. The concessionaire is an entity which is constituted by the design build contractor, but also the operation and maintenance and the facility management services, as you see below there. The concessionaire needs to fund themselves for the years that they need to build the project and maintain and operate it, because between the construction and the time in which they start getting revenues, they are exposed financially. And that's why equity partners are necessary, but as well as lenders like banks to give them the money to build up this at the beginning. The typical construction is maybe 4 to 5 years, and then the maintenance period maybe 20 years. After that time, well, they usually get back to the public authority. This is an example coming from the I-75 highway project that we're working on right now. Now, what happens in the first 5 years is that you may have some intermediate milestones because the government is also interested in you having the project done sooner than later. So they may pay a portion of your construction cost in order to reduce the exposure of the design and builder towards the lenders of money, and then reducing the interest of the payback that is being requested. This will transform in a 20 years of maintenance period in a reduced fee for the users, so for the public people, for the people that has to use that asset. But really what comes to the public-private entity for the concessionaire is the initial milestone payments, which are maybe covering less than 30 to 40% of the total value of the contract, and then the fees from the use of that asset. This happens for bridges, for tunnels, connecting underground sections, but also for non-transportation assets, such as water tunnels. And this case of the I-75 is having the highway, but is also having an underground tunnel, which reduces the flooding to the highway. And a value is given to the fact that less risk will be for the users using this highway because they will not risk to get their car into the floating highway one day. Now, the risk is very important because when we determine the risk of a tunnel, then we need to approach the financial institutions. We need to approach the banks and we need to approach the equity shareholders and ask them what will be your interest rate when we ask you the money. Now you see where the Michigan State and the case of the I-75 land to be in the Standard and Poor quantification of rating. The rating agency put him on an AA. It's a good one. So very small interest rate if they decide to borrow money from the market. But where do the stocks lower in an investment grade level? Because many financial institutions are thinking that we are a risky industry. They are not wrong, because what they say in the newspaper is always the damages, is always the issues. They never or not often enough see the successes of our tunnels. And that's where we come in the picture, and we need to try to reduce and convince them of reduced risks. That's why we need to identify those risks properly, which are geotechnical, geological, design development, on quantities of schedule, and contractual risk. Let's try to focus on the first one first of all. But first of all, let's get another sip of water. And let's think about what do you think of those ones is actually the most important for a tunneling project. Now, when we look at geotechnical and geological risk, we need to remember that they are a little bit unbalanced towards alternative delivery, because as I said before, in alternative delivery, in the design and build, this is very much on the contractor side. They need to get all of the risk for the geotechnical investigation. But the traditional DBB instead has a more time to develop the geotechnical investigation, but this translates also in longer schedule for the construction of the object. Let's look at the case history here that I'm looking at. We're looking at a saprolite formation, which has been subject to strong tectonic instability. That's the typical situation we have in the Deccan, in the Bangalore area, for example, where the surface is characterized by topographically moderate erosion elements. And really the bottom ground is instead a granitic bedrock intruded by a number of basic dikes. You know, the red laterite, which is on the top, is not usually found by tunneling. The tunneling that we have usually is in the middle area, where the bedrock weathering really proved to be the key factor for the tunneling condition. That was what happened in Bangalore. Like, the selection of the machine was critical for that reason. And you see here an example of how we selected the machine at the time. And the disc cutters were dimensioned in order to be able to cut boulders in soft soil, but also to be able to excavate in rock properly. The granite of Bangalore is one of the hardest rock that I have been drilling through in my experience after the Brenner-based tunnel granite, definitely. But it was important for us to select an air pressure balance type machine because of the closed mode. When we move into soil underwater, we definitely want to be able to move closed mode and not open mode, even though we may have the risk of finding rock sections and boulders at times. Now, this was not enough. And as some of you may remember, an emergency shaft was requested at a certain point because a boulder was encountered, which scrapped away from the cutter head of the machine all of the disc cutters, and the cutter needed to be substituted as well. So this is one example when having the right information on the geological side and having this risk over the contract to the contractor being responsible to find any possible solution to get the contract being running again. So in this case, the emergency shaft was excavated, as you see, very close to existing railway, and cutter was substituted, and tunneling was restarted, all at cost of the contractor. There was no possibility for claiming anything to the owner because the owner was not responsible for this geotechnical investigation program, and this is what design and build means, and that's why we need to convince the industry that we are capable of even the worst case situation like this one, find the right solution and get work again. And this is an example of when this was recovered. Now, another case coming also from the Bangalore station example, in this case was to identify exactly those rock levels. So an extensive campaign of probe drilling was enough to understand where the rock would have come. And you may understand what is the impact of having the rock higher or lower Accordingly, with the need of having secant pile, as you see in this case, protecting as support of excavations. Now, where do you end your secant pile? Definitely you want to embed this in rock. So that's why the level of rock is so important. And that's why having those probe drilling ahead of time was critical. It proved successful because really you may notice from the geological profile that dike was actually identified where it really was and allowed us to make a proper design that you see on the bottom right with tiebacks all the way through, and this was very interesting. Another example from the same project and speaking about the same risks comes from the station. The water table was actually considered to be a couple of meters below ground, and this is from the another station, Chikpa station. However, when we demolished all of the buildings which were above the area that the station would have come in, well, we noticed that the water table actually increased. And this is because of the fact that the houses were having shafts. The shafts were sucking water from the ground, and this was actually keeping the water table lower. But when we went to build it, the water table increased, and we needed to adapt our design and change our design. And that's what I told about before about risk mitigation and flexible approaches to be sure that we monitor what is on site and we are able to adapt our design. Some situations are actually very difficult to predict, such as the one of finding an ancient cannon from the Tipu era in your station. So you may have identified every geological and geotechnical risk, but you may have forgotten to read some history books. And remember that Sultan Tipu was actually moving cannons underground in a secret tunnel from the Tipu fort to the Tipu palace. And this was actually exciting because we found that cannon and we are now exposing this in the Museum of Bangalore. You see me there much younger 10 years ago. But the idea is some risks cannot really predict it. But that's when your design, your flexibility comes in a picture to make sure that you have a solution to recover an asset such as this one and save it away. The successful underground project comes definitely then from understanding the geology, but having also experienced and tunnel personnel around. And that's if everybody work as a team when the success comes in the picture. Now, this graph is very interesting because on a contracting arrangement, usually you may have initial spend higher for the geological investigation, which allow you to reduce overall the cost, but up to a certain limit. As you may notice, increasing the acquisition of data over a certain limit will not translate directly into reduction of total cost because it doesn't really address the risks of the project. And that's why building up an investigation program, which is progressively increasing the number of information, but at the same time, transforming those information into value-added design elements, it is critical. And as you may notice, at a certain point, this curve, the red curve, goes closer to an horizontal asymptote, which means we don't really gain additional information as much as we would need. So that's when it's critical to identify the risk and divide them into those that are related to hazards that are under an acceptable risk level and those that instead are not acceptable. And then focusing on that red portion. And this is an example from one of my projects where usually the unacceptable risk are less, maybe 14%, like in this case. Then you divide them. What are these 14% unacceptable risk level? Maybe our health and safety hazards, maybe our general hazards, maybe our environmental construction hazards. That's when we come in the picture and we try to identify them and mitigate those hazards only, forgetting about the others that are really under acceptable risk. And we focus our geotechnical investigation more efficiently when we really need it. Let's have a look at how an example from North America. Now we have a number of alternative, we have a number of variable geologies because we usually have the base rock, which is in this case Georgian Bay Formation or Queenstown Formation. And you may notice this is a shale, subhorizontally bedded. These have been subject to massive weight from the ice. 1,000 meters of ice on top of this rock compressed it in the past and created those locked in forces horizontally, which are now very risky. You may notice this is horizontally bedded, and for one reason, because it cannot crack on the vertical direction. These locked in forces coming from the memory of that big pressure from the ice. Now, on top of that, layers of glacial till accumulated with the moving of the ice from north areas. These actually created the most risk because in this glacial till we may find boulders, nested cobbles, sandy pockets, and that's when we move into tunnels maybe the highest risk. But when we hit the rock, well, we have to expect fault zones as well, and we have to expect those locked-in forces to trigger what we call the shale swelling, which is a time-dependent deformation that happens with time. So those type of risks should be very clear to us when we work in a geotechnical baseline report type of environment. So introducing the geotechnical baseline report was very important for the American Association of Construction Engineers, because really allowed to define exactly those risks which I mentioned before in an early stage of the project. This definition of the risks allow to understand what is the baseline for the contractor to bid on. So the contractor is not bidding for all of the risks possible that I mentioned before, but only for those that are identified early in the game by the owner and for which the owner is open to pay for. Everything above that level, if you find an unprecedented or unexpected geological conditions or a boulder that you didn't account for, well, then this is something that the contractor is not responsible for, because the contractor is only requested to quantify and cost the amount of geotechnical and geological information included in the geotechnical basin report. Don't get confused by the name. The Geotechnical Basin Report is not including all of the information you need for design. This is still up to us as designer and contractor to describe the parameters we want to design our tunnel for. The Geotechnical Basin Report is a contractual document. It gets in the contract and defines the major risks for the tunnel in order to reduce the exposure of the contractor when unexpected conditions are found. That's what a kind of unbalance again, the development risk during the design. Still on the alternative delivery side, still on the design and build, it's more risky because they have to take on themselves the selection of the parameters, even though a GBR may exist in the background. This is an example coming from Istanbul Metro. And speaking to the design risk, it tells you about the cut and cover structure, which was originally intended to be excavated across one of the major highways in the country, very, very crowded. And stopping the highway on one direction would have been massively critical for the economy of the area. That's why the tender project was having a large expropriation and a large cut and cover structure, which would have stopped this motorway. But when we went into bid, we decided to look also at other factors, such as the water pipeline that you see marked up there, which was a 3-meter diameter tunnel, which would have needed to be relocated. Utility properties are critical when we move from tender project to standard project. And looking at three-dimensional understanding of the station and all of the interfaces behind allowed us to look at the possibility of switching a cut and cover upper level of the station from the rest. And the revised project looks something like that. You see, there is no more need of stopping the motorway and not intercepting the water pipeline, because we were going to have a mine cavern underground and a disconnected cut and cover section just to connect to the surface in the expropriation area. We will connect on the other side. We connected on the other side of the highway through an overground walkway. These are the two footprints. Compare one on another to let you understand how the design changed and how a design and build is capable of doing this improvement from the tender stage to the execution phase, which allow value added for everybody, including for the owner. This is how the motorway would look like, and that's the station on the other side. This is the tunnel level, and that's the station concourse level doing with mined methodologies, SCM construction. That's how it would look like, the motorway in the middle, the shaft access on the left-hand side, and the station on the right-hand side, without interrupting the traffic at all on the motorway. The water pipeline was safe as well. Another example of how the design and builder can reduce the risk is on this TBM example from Bangalore. Now, the starting of the TBM is quite standard, you know. We have a shuttering pipe, we have a seal and ring, we have the possibility of pushing the TBM into that. Now, the seal and ring saves the construction from possibility of water inflows. But what about when we have to receive the TBM on the other side of the tunnel? Well, starting the TBM is quite standard, and you may notice from this case, we didn't have major problems. But when we receive the TBM on the other side, we usually have to create a jet grouting block. This is an example coming from another project from the U-Link tunnel construction. But in our case in Bangalore, we had an important Kote Vishamara temple, which was exactly above the area where we would have needed to create a jet grouting block to reduce the possibility of water inflows on the TBM breakthrough. This is the cross-section of the station, and the solution we found was that of creating a block of concrete inside the station, because it was not possible to create a jet grouting outside of the station to preserve the tempo. The block was long, at least a TBM shield and 2 additional rings, in order to avoid for water inflow to generate. And it was dimensioned to avoid the TBM thrust to push the block into the station, thus avoiding any risk of water inflow when a TBM would have come in. In the cross section, you may notice the block in blue, and it was dimensioned to resist against the water pressure that would have been generated between the shield and the concrete itself. Those water pressure transform into tension forces, which were covered by the use of steel rebars in that area. Now you see the concrete block being cast in here. Then the TBM breaking through, and you see some water comes in. This is the water between the shield and the concrete block. But then after the first water coming in, there is no more water. The water stops coming in because we actually achieved the sealing between the segmental lining, the bicomponent grout injected between the segmental lining and the ground and the concrete outside. And with our gasket, we have no more issues. So I remember that we went on several of the newspaper at that time when Kaveri banks it in, and then the second TBM also managed to get her way into the station, and I would say quite successfully with even less water. Now the problem here was demolishing this freaking concrete block. You may see here it was quite an intense work to be done, but that's why you need to dimension this concrete block with a low grade type of concrete. An M15 would be enough, so that it resists on the short term, but it's easy to be demolished. The demolition took place, and then it finally was cleared out. So this tells us that really the risk management plan is affected by the procurement method, giving the freedom to the contractor to make their choices on site and applying them, allow them to deliver innovative solutions. In this case, was quite new, and at the same time, succeeding and respecting the construction schedule, even in challenging times. So that's the strategy of success, moving from input data into the underground design, monitoring the conditions, and then design optimizations that are flexible enough to respond to our risks on site. And translates into different matrices for tolerance criteria. I've prepared a couple of papers on that, which I would suggest you read. And if you want to be in contact with me, I can provide you with them. But the risk matrices really need to be modified accordingly with the risk exposure of the owner and the contractor on the environmental side, on the construction side, on the social risk and health and safety as well. And you see here, every matrix is different as we approach different type of risks in a different type of risk tolerance scenario. The strategy of success is definitely that of risk managing all of the risks, but understanding also how the geological and geotechnical aspect may affect our construction. And the alternative delivery projects allow for the risk sharing principle and design build engineer and design build and the owners itself, so that everybody is really aware about what risks they have to take on and how do they quantify them in money value. That's why along a project life cycle, we need to look after the business case stage, the conceptual design through testing and commission and final utilization. But the detail and design and construction stage is the one in which we really can quantify the risk for the owner and for the contractor as well. I think I'm almost on top of the hour here because I'm looking, we're already a lot into that. Let me try to focus on the last few concepts here. The digital delivery is critical because it's what allows us a full-time monitoring of all of the situation on site and an ability of addressing any problem on site and resolving them quickly. That was my third sip of water and my pour for on how you deal with digital delivery. And if you're really following the digital transformation across your companies, I would like to see if I have more time. Can anybody from the organizing committee tell me how much time do I have left to get a couple of more concepts through? Guys, how much time do I still have?
I understand we can continue for about 15 minutes more, then we can have question answer session of 15 minutes.
That's perfect then, because I'll wrap it up because we started a little bit later. I want to wrap it up with just one more case history. I was having not many slides yet, so I'll just wrap it up with these responsibilities.
Maybe 15 to 20 minutes. You can have continue with your presentation, and then we can have subsequent to that we can have question answer session.
That's perfect. Thanks a lot. I'll be on time. Perfect. So I want to deliver this one more concept, and I have a couple of more examples. But it's critical to understand roles and responsibility of the contractor and the owners and the engineers. Traditional DBB, what we call tradition in the United States, which is the one that allows full geotechnical and design responsibility on the owner, is quite clear. You see, there is a clear definition, 2 boxes only. Owners and engineers are responsible for risk on geological side and for the design. Contractor is responsible only on the contingency. So the idea here is the contractor has a problem on site. What it is fault as far as the means and methods he adopted were wrong. But if he respected the design and the geological constraints from the owner and the engineer, well, this is not his responsibility. On alternative delivery is a lot more complex. There are 3 cells here which are kind of identifying to you a gray area in between an understanding of the geological conditions at the beginning, at the bid stage, and what are instead responsibility later on from the owner's side. It is quite complex and not often allows avoidance of claims. You know that in design and build, we are often dealing with claims and issues like that, which on a design bid build instead do not exist because it's a more clear definition of risks distribution. There is another example coming again from the Bangalore Metro on how this translates into practical issues when we look, for example, at the induced settlements from ground excavation. And as you may know, when we excavate the ground, we induce tensile and shear deformations on the existing buildings. And box cutting and cording chart here below on the left-hand side allow us to identify a clear risk on the buildings, which is from negligible to very severe. And on the bottom right side, you see how we usually define them on a twin tunnel. When we have identification of buildings under moderate or severe risk, then we need to do something about it and moderate such a risk. In this case, you see we were underpassing a very ancient temple, a complex of temples actually, and the induced settlements that you may notice on the left-hand image were very high, were higher than 50 to 60 millimeters, meaning that the building was at risk. You see on the right-hand side, the horizontal displacement and the deformations were actually leading towards very high tensile forces on the foundation systems and definitely risk for cracking. And this is where the building is located, where you see my red mark on the bottom. Now, remember that we were always excited about that. This was the puja that we did for the starting of the TBM. But what I discovered also was the importance for the religious respect of the area. A temple cannot be just shut down. And I learned my lessons when I was working on this project. And what I needed to do in that case was trying to find a way to keep the temple accessible and to keep the religious events open by simply having a strategy towards the health and safety of users of the facility. So alternative temporary door entrances were created to avoid the main door. Propping sections were done, and an intense monitoring strategy and plan was created with alarm and sounds being generated in case we overpass some threshold values. The temple was protected and it was quite safe. However, some of the risks that I want to highlight is that not often we are so lucky. Sometimes we see damages such as those ones, and those are typical from settlements happening under the foundation of a building, which induce those shear cracks on corners of buildings. And we have to check all the time what happens in the ground. We need to check if the gap between the tunnel and the ground is properly filled. And not only I would suggest to check the pressure. You see in this case, the pressure was quite good. We were injecting at the right pressure, the bicomponent grout on the tail skin, but the flow rate was almost zero. So this means that we really were having some stuck hoses for enough flow to get into the the tail skin, and this meant that we were not actually injecting the bicomponent grout, and maybe this was the reason why we were creating additional settlements and possible impact on the buildings around that. When we looked at the Brenner Base tunnel, we looked at a twin tunnel with an exploratory tunnel in the middle and cross passages all the way through. The interesting portion of this is that it's fully in rock and excavates through the Peri-Adriatic fault, which is below the Alps between Italy and Austria. And it is a very active fault moving east to west, while our tunnel would go north to south. Now, when looking at the performances of different type of TBMs, I needed to select what type of machine to use. And we were comparing double shield open TBM and one shield TBM. Again, this is something that you don't want to prescribe as an owner. You want to leave this to the contractor, because the contractor is the one finally responsible to drive the TBM through such a variable geology, as you may notice in the bottom, up to 2,000 meters of rock on your head. And you want to make sure that the contractor is responsible also for the performances in terms of meter per day they can advance. So you may notice those curves with different type of uniaxial compressive strength, either below or above 45 MPa. I found out that they were having a complete different behavior. So the double shield TBM is actually always increasing as we increase our RME value. You know, this is Benyaski defined rock mass excavability parameters. As we increase that, which means we're getting on a better rock, the double shield is always increasing. But that is not the case for a single shield TBM. The single shield TBM top up and stay stable. The average rate of advance, the ARA, is actually stable at a certain point. And the open TBM is outperforming every shielded TBM, but only if we have strong rocks, if we have uniaxial compressive strength above 45 MPa. Again, this is a case history that I learned, but it speaks to the responsibility of the contractor being the one capable of choosing the right machine, because they have the data of how their machines perform in the past. You as an owner may not have it. And when we work for owners, we need to remember that. This was the case of the contractor also when encountering an issue. So you may notice average rate of advance were always quite on the bottom right end. So meaning that in an early time between February 2008 and July 2009, they were performing quite well, between 15 to 40 meters per day. Now, the different colors of those dots show you different type of rock condition, different type of RME values. So, you know, they were quite standard, very scattered. I couldn't find a real rule to say what rock would have been better excavated and faster excavated. However, we stopped for 4 months. We found a parallel fault to our tunnel, which stopped for 4 months the excavation. When we restarted, the machine was not looking as good as before. You look at the performance from January 2010 above, they were much lower than 7 meters per day in average rate of advance. This means, again, that if the fault would have been identified before, in this case from the initial geological owner responsibility, then the TBM could have performed well enough later on. And that is, again, where the responsibility of the owners come in the picture. So the contractor to choose the right machine to excavate is to be exposed to that selection. But then what about the risk of finding an unexpected fault and putting at risk the workers? So this is where we really have to be careful, because we expose ourselves to claims, or we have an opportunity for claims, depending on which sides we're sitting in. This case was ending up with the owner paying for the fact that the TBM was advancing much slower. So they couldn't apply any penalty to the contractor, because it was actually not their fault, and the machine was performing well before the stop, but then they needed to stop because a fault was not identified by the owner in the early geological investigations. So this really drives me towards conclusions on risk sharing principle in alternative delivery project. Owner always owns the ground, regardless. And that last example tells you, even on a design and build environment, at the end of the game, if something was wrong in the ground, the owner will pay for it. Worst case scenario, the owner will not have their tunnel built on time, and they cannot tell to the social risks that they will have their asset done, so people will not be able to use it. So if you remember the matrix I showed you at the beginning, we are on the top left quadrant, the social risk is in the case. A solution may be found by introducing the GBRB during bidding phase and the GBRC during construction phase. So everybody bids on a slighter amount of geotechnical information included in geotechnical basin report B. Once the awarded contractor is selected, then together with the owner, they prepare a GBRC, which includes more geotechnical information and is agreed and signed off by both, so that the design build team will not have to claim if they find some unexpected conditions on site, but they can early on in the game agree on a financial closure where more money are allowed to deliver this project. So this is the innovation that has been brought recently, and that I suggest we also follow. I'm not going to walk you through this losing and winning scenario. More or less is what I just expressed to you. But I want to have a final remark on successful projects, which are always connected with how we deal with risk management, regardless of the procurement method we're looking at. So how do we balance the geological, geotechnical, structure performance information, and how do we balance instead the supervision, the monitoring, the workmanship ability, the interpretation of the ground? All of what you see on the right side may be less important at the beginning, but is actually as much important as what you see on the left-hand side. It's not just about the information and the choice of appropriate means and methods, but it's also about identifying the hazards and having the right solution for them, mitigating them in the best way possible for the entity which is driving the contract, which is the contractor or the design and build entity or the P3 the P3 concessionaire. So with this one, I would like to ask you questions, and I will leave you with this image of our recently concluded Hong Kong tunnel with the largest TBM in the world, which is the Czech Lapcock link. Thank you very much for now. Are there any questions? How do we work for questions? Should I read them or?
If there are any questions, please raise your hand, and we can address it directly to Mr.
Giuseppe.
Gaspari. Any questions?
This is Parikshit. Hello.
Yes,
hello.
Mr.
I wanted to take your opinions on the Emerald Book. What do you think is how good is the Emerald Book?
I think it's a very good resource. As a matter of fact, you anticipated my next slide, where I was recommending some guidelines for risk sharing. So 3 books for me are very important. The Recommended Contract Practices, which is by the Society of Tunneling in North America, the GBR, which I mentioned before from the Association of Construction Engineers, and the Emerald Book. That is definitely a new resource by FIDIC and the ITA, the Tunneling Association, International Tunneling Association, sponsored that. Most of what you have heard today is coming from experience, but is also consistent with what the Emerald Book says. So really, I do agree with what is included, and I do suggest these 3 readings if you're interested in the subject to inform yourself and prepare yourself.
I have one more question. We do a lot of tunneling in the Himalayas. Most of it are deep tunnels. And the issue with most of these longer tunnels is that we do not have access for exploration. We actually cannot make these rigs reach those places and to give us geotechnical data through geotechnical investigations. Again, we do a lot of geophysical investigations, but I personally believe that they have severe limitations as far as. So how do you think should we go ahead? I want to ask you particularly, do you think that we should push monitoring and observation as a practice, because that is the only way for us to go ahead, have advanced rates and probably advanced rate matrix and do tunneling like that in places like the Himalayas where exploration sometimes is not possible?
This is a very interesting question. Thanks for asking that, actually. Now, let's divide the answer in either a procurement method where the owner designed a tunnel and a procurement method where the tunnel. So in the first stage, the owner designed a tunnel has one great advantage. Property access may always be easier for a public entity to get. You know, expropriation is an available tool. Purchasing the property, convincing the owner, political pressure. There are several bullets that that the public entity can adopt. So for a design bid built traditional type of delivery, it's quite easy to access from the surface. And I do agree with you, geophysical investigation are super useful, but they are always meaningful if they are connected with physical boreholes. So I may have a strong length of geophysical, but I need to have at least a couple of boreholes, to fix the target, to somehow have a confirmation of what I get from geophysical investigation. The other side is the design and builder. When you are a contractor, you don't have the time to negotiate with a public and with an owner of a land to have access. And sometimes you didn't even want to do that because it's more risky and it's more costly. So what you do is really using some probe drilling from the tunneling, from the TBM or from the SEM excavation. It has also limitations. I may suggest you a paper I also wrote some time ago on those investigations from TBM. There are the beam method, and if you're aware about that, that allows you to inspect ahead of the cutter head and see if you're actually finding some pockets of sands, some pockets of water. And again, it has been proving successfully maybe 60-80% of the time, not always. So we have additional methods that speaks to the observational method, as you mentioned before, that we can use if we cannot access the surface for proper investigations. However, we were running all of them, but imagine you are in the Brenner Base Tunnel, 2,000 meters of rock ahead of you. You only have maybe 5 to 6 boreholes because it's 2,000 meters long boreholes. So you cannot do as many as you like, but you have to drive your tunnel for 14 kilometers, right? And you only have 5 boreholes, not many at all. So that's the case in which you really need to have investigation ahead of the surface. It's not about properties. It's just about not being possible doing more of preliminary investigation. And that's when we decided to have a, a geotechnical exploratory tunnel. So the large high-speed railway tunnel of the Brenner Tunnel, the longest in the world, are about 8 to 10 meters in diameter. But before excavating those big tunnels, we did a smaller tunnel, the exploratory one, which is only 6 meters in diameter, smaller, and doing a lot of prospection ahead and trying to understand how the ground would have behaved. That tunnel is the one I showed. Tunnel identified a fault which was parallel to the alignment, so impossible to be detected ahead of the cutter head. But that fault was very important to be understood with this exploratory tunnel because it allowed us to properly design the bigger tunnels, the 2 large tunnels that I showed you before. So that was the slide I was referring to, and I hope this answers to your question. You see the exploratory tunnel in here. We couldn't have many information before taking a big risk on the big tunnels. We took a smaller risk on a smaller tunnel to run in between. Again, this is the biggest tunnel in the world, so we could have allowed to spend the money for an exploratory tunnel. Sometimes you cannot do that, and you have to rely on probe drilling or beam method or other technology from the tunnel itself.
One more question I'd like to ask you, just from your experience. What do you think is what depth could a geophysical survey give us confidence about? How much of depth?
I know that new technology allows to go very, very deep. In my experience, 40 to 50 meter, maybe 60 meters deep is what I have been using in urban areas for geophysical investigation in urban areas. That's what I rely on. But I know that the technology is now pushing forward the limit.
Mm-hmm. Especially the aerial electromagnetic surveys, because we do not have too much of experience here in India, and I for one believe, because it's basically mounted on an aerial vehicle. Do we actually get? Can we? Should we depend on that data a lot, especially more than 30 to 40 meters below the surface?
Yeah, when you're in the mountain area, you need to go much deeper. You need to go much larger. But that's when the cross-hole information maybe it's probably more useful than a geophysics from the surface, right?
Yeah.
Cross-hole or downhole maybe help you more.
Perfect. Perfect. Yeah, I just wanted to ask. Thank you. Thank you so much.
Oh, no problem.
Sir, there is one more question in the chat box.
Sure.
Mr. Trivedi wants to ask, to what extent geotechnical risks are addressed in mineralogy? I think that probably be okay. Another question. Any further questions, please?
I don't know if I heard a question about geotechnical investigation, but I didn't get.
Gargi Mishra she has raised her hand. Ms. Gargi,
This
can
is
you?
R.K. Mishra. Hello.
Hello,
This is R.K. Mishra. I'm
Ms.
from
Mishra,
NHBC.
can you please ask your question?
Sir, I just want to know whether with GBR, should we have additional parameters also like possibility of ingress of water, rock busting, etc. Other conditions should also be included, or GBR is good enough?
So the GBR always has to include everything which put at risk your tunneling. So what you mentioned before is definitely something that has to be in the GBR. It has to be. So what is not in the GBR is the parameters for you to design. So the GBR includes rock bursting risks, includes boulders risks, includes the swelling potential. All of those information are in the geotechnical baseline report, so that you can select the right tool, the right TBM. You can mitigate the risk in the right way. What you don't find in a GBR, because it's not the responsibility of the GBR, is the cohesion, the friction angle, the elastic modulus, the uniaxial compressive strength. If you find them in the GBR, they are always in a wide range. They always give you a big statistical variability, but they don't tell you this is the parameters for you to design, because it is always, in any case, the responsibility of the designer and the builder to develop them.
Sir, one more question I have actually. Suppose that there are deviations with respect to GBR, then how it will translate into the claim? There may be deviation in RMR values and ingress of water. So how it will relate to the claim?
You quantify them. I give you an example for ingress of water. In the GBR, when you are the engineer preparing the GBR, you need to tell exactly how much water you're expecting, 1,000 liters per minute or whatever, right? If you find 1,200 liters per minute, then you claim to the owner 200 liters per minute, because it's the difference between what you register and what is in the GBR. So that is a fair way to split and to be clear about the claims. So nobody will argue, and we don't have to pay years and thousands of dollars or rupees to lawyers, because it's very clear. If I say in the GBR, I have 1,000 liters per minute of expected groundwater inflow, and then you find and you measure 1,200 liters per minute, then you're going to claim for the extra difference.
So it will ultimately correlate with the progress of work. Suppose that there is not much change in the progress. Will the contractor still be able to lose claim?
If the contractor claims for something that he doesn't have the proof for, yes, the contractor will lose. But if the contractor asks a claim on something that is really different, what is included in the GBR, and has a proof for it, contractor will easily win. And the owner will be happy to pay for it. Because really, if the owner doesn't pay for it, the contractor doesn't have the financial ability to move forward. That's why my presentation I started with the money. With you go to the banks and to the equity shareholders and you ask for money. But you ask for money accordingly with the GBR. If the GBR, I mean, if the conditions are different than the GBR, who would you ask the money to? You would just go bankrupt and nobody wins, because the project doesn't get done and and really the owner doesn't have any win. So it's a fair share. The owner is also interested in having a fair share of risks and allocating the money in the right way. Because if not, he doesn't get the project on time, or he doesn't get the project at all.
Thank you. So nice of you. Thank you.
Thank you.
Could
I see
I
one
ask?
more question.
Could
Any
I
more
ask
questions,
another
please?
question, please? Yeah. I wanted to ask you generally for deep tunnels, what is the kind of contingency funds which are catered in percentage, if there is a ballpark figure like that?
You asked me to be a magician. So the contingency very much depend on the contract. And again, that's why the GBR is important. One more time, because if you see the GBR that the owner doesn't detail very much, then you have to increase the contingency. I give you one more example: boulders. So you are in a glacial till, or even imagine Bangalore. I mean, we are in that situation in which we may have found boulders. How do you quantify the number of boulders you find? Imagine that machine that stopped. How many times does my machine need to stop because I have damages induced by a boulder? So in some GBRs, the investigations are so many that you can actually say you will find this dimension with this average uniaxial compressive strength. You will find 60 boulders with a smaller equivalent diameter with these different UCS. So some GBRs are capable of introducing an exact number and an exact characteristic of all of the boulders because they have extensive geotechnical investigation. They could run them. But some other GBR cannot do that. And that's when you as a contractor instead need to come in the picture and increase your contingency. So I've seen contingency being as small as 5 to 10% when the GBR is very clear on how much you should consider in your budget. So this is not a contingency. This is real money that you will really spend to remove the boulders or to refurbish your tibium if you hit some of them because they are included in the GBR. But in other cases, you need to increase your contingency up to 50% or more than 50%. Like in the case of the Brenner Tunnel, we didn't have many information geologically. We were running an exploratory tunnel, which was a very high risk because we were kind of trial and testing, observing, adapting our design every day because we didn't really know what we would have found. And that's when the contingency are as high as 50% or more. But that's when sometimes, if contingency are so high, then the owner may decide to go into a different type of procurement method. Because why would you be having such a risk of doubling up your cost of a tunnel and not controlling why does it increase in cost? So that's why you probably want to move into a different procurement method. Instead of design and build, maybe do design bid build or early contractor involvement or other forms of alternative delivery. Or even time and material, maybe a choice, right? So this is happening when contingencies are too high. So when you don't have enough confidence on the ground on the information you have.
So thank you, Mr. Gaspari. I am on behalf of Tunneling Association of India. We are really thankful for making a very exhaustive presentation, which I hope our participant would have been benefited a lot. We look forward for many more such interaction in the near future. We will be in touch with you and certainly work together. Thank you very much.
But I want to thank you, everybody. This was an amazing workshop and amazing questions, great interest. And I miss India so much, guys. So you made me feeling back home sometimes. I lived for 5 years in India and I still miss it. So thanks very much for having me today.
Mr. Gaspari, we are next year that ITA award function and Tunneling Asia conference will be held in Mumbai in the month of November. So we certainly look forward for your active participation in that
I
conference.
will be happy to.
Yeah. We will be in touch. Thank you very much.
Thank you very much to you guys.
Yeah.
Have a good evening.
Okay, same to you. Yeah.
Thank you, Mr. Gaspari. Thank you so much.
Bye-bye. Take care.
Thank you. Bye-bye.
Thank you. Thank you. Thank you.
Bye bye, everybody.
Bye. Bye.
Thank you so much.